Welcome to the deep dive. Our mission today, well, it's pretty focused.
Mhm.
We need to unpack how we get these huge context windows in AI. I think 128,000 tokens, maybe more, without the cost going through the roof. We're digging into a technical report on the Ring Linear model series,
Mm.
specifically Ring Mini Linear 2.0 and Ring Flash Linear 2.0. The big question is how this hybrid architecture they developed managed to slash inference costs so dramatically, like down to a tenth, while still keeping performance, top-notch for complex reasoning.
Yeah, and this research really hits a nerve in terms of what industry needs right now. If you think about where things are heading, advanced agent systems, complex code generation, they all fundamentally need lots of context. But if you just stick with the standard ways of building these models, the resource demands, the sheer cost, it just becomes unsustainable for, widespread use. So this report is suggesting maybe it's not just about scaling bigger, but scaling smarter architecturally.
Okay, so let's start there. What's the main bottleneck, the big headache that Ring Linear is trying to get around?
Well, the core problem really lies in the standard attention mechanism of softmax attention that most LLMs use. Its computational costs, it doesn't just grow linearly with sequence length, it grows quadratically. So Omen 2FDA, think about it like this. You double the context length you want to handle, and the compute needed roughly quadruples. It gets out of hand very fast. And then there's the I/O overhead, managing the key value cache, the model's memory, basically. That grows linearly with the output length. So pushing past, say, 8K or 16K tokens just becomes incredibly expensive, resource-intensive.
That quadratic scaling sounds brutal. So, okay, the research community didn't just sit there. They explored linear attention, right? Things like RetNet, lightning attention. These promise much better scaling, more like $20 tied more to the model size than the sequence length squared.
Yeah.
Seems like the obvious fix. Why didn't everyone just switch?
It turns out, well, it's not quite a silver bullet. And that's really key to what this report is getting at. Pure linear models, while they solve the theoretical scaling issue and have this nice constant space complexity for the KV cache, they often just don't perform as well, especially when you scale them up to the sizes needed for industrial applications. The quality, the expressive power can lag behind. Plus, there's this sort of practical catch, the theoretical efficiency advantage. It often only really shows up when you get to really long sequences, maybe beyond 8K tokens. For a lot of typical training tasks, the benefit just isn't big enough to make up for that potential performance drop.
Okay, so that's where Ring Linear comes in with its big idea. Don't go pure linear, go hybrid. That feels like the crucial balancing act. Keep some of that high-quality softmax attention, but use linear attention for the heavy lifting, efficiency-wise.
They're trying to get the best of both worlds, basically. Balancing the expressiveness of the standard approach with the resource savings of linear. And to show this works, they've open-sourced two models built this way. There's Ring Mini Linear 2.0, which is 16.4 billion parameters total. Still pretty big, but manageable. And then there's Ring Flash Linear 2.0, a huge one at 104.2 billion parameters. But the really impressive part, the thing they both share, is that they both support 128,000 token context length.
Okay, 128K context is serious. How did they actually mix these attention types? What does the structure look like inside this hybrid ratio?
They didn't just mix them randomly, they came up with a specific layer grouping system. So the layers are in groups. You have one softmax attention layer, and it comes after a set number, let's call it a baller, of linear attention layers. They tuned this ratio. For the big one, Ring Flash Linear 2.0, they found a group size of 8 worked best. That means $1 is 7. So 7 linear layers, then 1 softmax layer, repeat. For the smaller Ring Mini Linear 2.0, the group size is 5, so the $1 is 4. 4 linear layers, then 1 softmax.
Interesting. So most of the layers, like 7 out of 8 in the big model, are the efficient linear type. The softmax layers is used more sparingly. The report also mentions they use a sparse mixture of experts, MoE architecture, with a 132 activation ratio.
That's right. They incorporate MoE as well, which adds another layer of efficiency by only activating a fraction of the experts for any given input. But even within the attention layers themselves, they made some key design choices for optimization.
Right, beyond just the hybrid structure. What were some of those component-level tweaks?
They highlighted 3 main ones that really added up. First, grouped RMS norm. This is about optimizing communication in distributed training. By doing the normalization calculation locally within each GPU rank or processing unit, they managed to completely get rid of the all-reduced communication step in both the forward and backward passes under tensor parallelism. That cuts down a major communication bottleneck, which is often a huge limiting factor in large-scale training.
Okay, that speeds up training. What about things that affect the model's actual reasoning ability, like handling position?
For positional information, they used rotary position embedding, or ROPE, but they added a twist. They only applied ROPE to half of the dimensions within the linear attention module. It might sound small, but they found this tweak gave them a measurable improvement, about a 0.004 reduction in the training language model loss. It shows how these fine details matter. The third thing was about how the hidden state decays in linear attention. Instead of a simple linear decay rate, they implemented a headwise power law decay. This was actually quite impactful. It led to a much larger reduction in training loss, around 0.04. So a better decay model meant better learning.
Those architectural details are fascinating. But okay, let's get back to that headline number, 110th the inference cost. How do they achieve that kind of raw computational speed up? It can't just be the architecture, right?
No, it required serious infrastructure work, too. That 110th figure is compared to a standard, say, 32 billion parameter Benz model, and it's over 50% cheaper even than their previous Ring series, which was all softmax. A huge part of this came from developing their own high-performance FP8 operator library. They call it library-linghe. Just implementing this FP8 library, which allows calculations using 8-bit floating point numbers instead of 16 or 32, improved their overall training efficiency by 50%.
Wow, a 50% speed up just from changing the number format and optimizing the operations for it. That's massive. And this Ling library you mentioned, it uses kernel fusion heavily. Can you break that down for us? What is kernel fusion?
Sure. So on a GPU, computations happen in small steps called kernels. Kernel fusion is basically a technique where you combine several of these small sequential steps into one single, larger, more optimized step. The benefit is twofold. First, it reduces latency because the GPU doesn't have to constantly stop, write data to memory, read it back for the next tiny step. It just does more at once. Second, and really important for training big models, it reduces how much activation memory you need during the process. Less memory usage means you can fit bigger batches of data onto the GPU at once. You can increase your microbatch size or MBS.
Okay, so fewer stops, less memory shuffling, bigger batches. Could you give an example of what they've used?
Yeah, they gave a good one for their linear attention layers. They took several operations related to the gating mechanism, things like transposing the attention output, doing the group RMS norm, applying the gate sigmoid function, and then a multiplication. And they fused all of that into a single custom kernel. This was apparently very effective, letting them use those larger microbatch sizes, which directly translates to faster training throughput.
Makes sense for training. How does this efficiency play out when the model is actually being used at those really long context lengths? What do the benchmarks show?
The throughput numbers really back up the claims, especially as context gets longer. For what's called pre-fill throughput, that's processing the initial prompt, Ring Linear starts pulling ahead of their older Ring 2.0 model, the softmax only one, once you get past 8K tokens. But when you push out to 128K tokens or more, Ring Linear isn't just a bit faster, it's achieving over 2.5 times the throughput of Ring 2.0. And compared to standard dense models, over 8 times the throughput. And for decode throughput, how fast it generates the response, the gains are also huge. At 64K context, Ring Linear was more than twice as fast as Ring 2.0 and over 10 times faster than the baseline models.
Okay, the speed is clearly there. But you can have the fastest model in the world, and if it falls apart during fine-tuning, especially with reinforcement learning, it's not much use. This brings us to their work on stability. The report talks about this training inference disparity. What exactly is that, and why is it such a problem for RL?
Right, this is a really tricky issue. The disparity happens when the exact implementation of certain components, think RMS norm again, or ROPE, or even just how floating point math is handled, differs slightly between the software framework used for training and the one used for inference, for actually running the model. These tiny differences, maybe in numerical precision or calculation order, they can seem insignificant. But in these deep networks, especially with things like MoE or the recurrent nature of linear attention, these small errors can accumulate layer by layer. During RL fine-tuning, which often relies on the model's own prediction on policy, if the model behaves slightly differently during inference than it did during the training rollout phase due to these disparities, the whole learning process can become unstable. It can even collapse entirely.
So it's like the model is learning based on one set of rules during training, but then playing by slightly different rules when it's actually used, causing chaos. How do they fix this? What does systematic alignment involve?
It basically meant going through everything with a fine-tooth comb and ensuring identical implementation and, crucially, identical numerical precision across the board. For example, they discovered that in their linear attention, the internal state accumulation absolutely had to be done using FP32 precision, 32-bit floating point. If the inference engine defaulted to something lower, like BF16, for the key value states to save memory, the numerical errors would build up over long sequences and cause divergence. So they enforced not just the same algorithms, but the same precision and calculation details for all the critical modules. The KV cache, the final LM head output layer, RMS norm, the attention mechanisms, ROPI, everything had to match perfectly between training and inference environments.
That sounds like a painstaking process. Did achieving that level of alignment simplify things when it came to the actual RL algorithm like PPO?
It seems like it did. Once they had confidence that the model behaved identically in both settings, they found they could use the more straightforward, theoretically sound approach for PPO. Specifically, they could directly use the probabilities calculated during the training rollout phase within the PPO clipping mechanism. This apparently gave them higher rewards and better stability compared to a common workaround. Often, frameworks have to recompute probabilities during the PPO update step, specifically to try and compensate for that known training inference disparity. By fixing the root cause, the disparity itself, they could use the cleaner, more direct PPO formulation.
Okay, so they achieved massive efficiency gains through the hybrid architecture and infrastructure work like FP8 and kernel fusion, and they ensured stability through meticulous system alignment. But the ultimate question remains, did all this focus on efficiency compromise the model's core job, complex reasoning? How did these ring linear models actually perform on challenging tasks?
That's the crucial test, right? And the evaluation results seem really strong. They consistently hit state-of-the-art or SOTA performance across several tough reasoning benchmarks, even with their relative efficiency. Let's look at the smaller one first. Ring Mini Linear 2.0. It's 16.4 billion parameters total. On AMI 25, which is a benchmark for advanced math problem solving, it scored 73.65. That's actually higher than a competitor they listed, Qwen 3.8b Thinking, which got 71.25. And on Code Forces, which tests coding ability via competitive programming problems, Ring Mini Linear got an ELO score of 83.84, significantly ahead of the Qwen model 73.31.
Okay, so the smaller model punches above its weight class, it seems. What about the big one, the 104.2 billion parameter Ring Flash Linear 2.0?
That one performed even better, holding its own against much larger models. On that same AMI 25 math benchmark, Ring Flash Linear scored 86.51. Compare that to Qwen 332b Thinking, a larger model, which scored 75.47. And on a really challenging benchmark called GPQA Diamond, which tests expert-level general knowledge and reasoning, Ring Flash Linear scored 74.49, again surpassing the Qwen 332b model's 68.40. So yeah, the results seem to validate their core idea. They managed the efficiency and performance trade-off successfully.
So, to kind of wrap this up, the Ring Linear series looks like a really promising direction. They've shown that this hybrid architecture, keeping some softmax attention but relying heavily on linear attention, and combining that with serious infrastructure work like their Ling FP8 library, kernel fusion, and that meticulous system alignment for RL. It allows them to handle massive 128K token context / inference costs down to maybe 110th and still deliver top-tier performance on complex reasoning tasks.
It's definitely a very strong piece of engineering, though it's worth noting they were upfront about remaining challenges in the report. They mentioned two key areas for future work. One is that in their current linear attention module, the query, key, and value projections still have the same number of attention heads, which apparently still leads to significant memory overhead. Optimizing that could yield further gains. And the second point is, well, those softmax attention layers they kept for performance. They still represent the main computational bottleneck remaining in the architecture. Reducing reliance on them further is the next frontier.
Right. Which leads to a really interesting thought to leave our listeners with. We've seen how this hybrid approach unlocked huge efficiency gains while keeping performance high and stable. So thinking ahead, how might the ongoing push to minimize or maybe even eventually eliminate that remaining softmax bottleneck fundamentally reshape how we build and deploy these incredibly powerful long context language models in the near future? That really feels like the next big puzzle piece to watch.